Hi and Assalamualaikum. We are from Group 5 and we will be presenting about the flight scheduling using Google or our tools. We have 5 members in the group and these are the members.
Assalamualaikum. My name is Muhammad Adam Iman bin Ahmad Junaidi. I will present the introduction of the study and the flight departure scheduling model. The data used in this study were collected from the Malaysia Airlines Flight Status website, focusing on flights departing from Kuala Lumpur International Airport (KLIA) on 10 January 2026. The dataset includes two main attributes, the flight number and the scheduled departure time. This study focuses on solving an aircraft departure scheduling problem using graph theory. All selected flights depart from the same runway, namely runway 40L/22R, which creates potential scheduling conflicts due to overlapping departure times. A total of 16 flights were identified within the time interval from 7:55 to 9:10, as shown in this table, which lists the selected flights number and their corresponding scheduled departure times. Next, for this figure, illustrate the adjacency matrix used in this scheduling problem. In this matrix, the rows represent flight numbers while the column represent departure time slot, which are divided into fixed 5 minutes intervals. An entry of 1 indicates that a particular flight is assigned to depart at the corresponding time slot, whereas 0 indicates that no departure is scheduled at that time. This adjacency matrix is constructed to identify potential conflicts and scheduling overlap among flights occurring within the same time slot. Using this adjacency matrix, a bipartite graph can be developed where flight numbers and departure time slot are represented as two distinct sets of nodes. This systematic scheduling approach has prevent overlapping departures, improved runway utilization, and reduced the effort required for manual scheduling.
Hi, my name is Laila Atira and I will be presenting about the problem overview. This project addresses time management issues in aircraft departure scheduling. Currently, 60 flights are scheduled to depart from KLIA using the same runway 40L/32R to different destinations within the same time period. When multiple flights are scheduled to depart simultaneously, operational problems such as delays and congestion may occur. To illustrate this issue, an adjacency matrix is used where one represents flight departing during the appointed time. The result highlights scheduling conflict, indicating the need for a structured solution using graph theory.
Next, I will explain the objective of this study. The first objective is to construct an adjacency matrix that represents the flight departure schedule and to identify potential timing conflicts on runway 14L/32R. The second objective is to model the aircraft departure scheduling problem using graph theory, specifically through the application of bipartite graph, where flights and departure time slots are treated as two separate sets of nodes. The third objective is to restructure the adjacency matrix into a one-to-one flight to slot assignment in order to generate a conflict-free departure network diagram. Finally, this study aims to provide a basis for recommending a better scheduling strategy that can help prevent departure clash and reduce potential delays.
Hi, my name is Omar Anwar, and today I will explain how we use Python with Google OR tool to solve the scheduling problem regarding the multiple aircraft flight number clash at the same departure time. The first step is supply the framework needed. So the first framework is NeoS was applied to model the problem as a connected system. Each aircraft flight number and scheduled departure time was treated as a node, and conflict were represented as edges. This approach makes it easier to detect clash and organize the schedule by bipartite graph. Second framework is Matplotlib Pilot, which was used for visualization. It helped display the graph clearly, showing the relationship between aircraft flight number and their scheduled departure time after processing by NeoS. The second step is define the left partition, right partition, and requested time. The left partition will include all the flight number that depart in the specific time and defined as NH, while time is where we include all the time departure available, and requested time is when the original time of flight number take off.
Step 3. Assign nodes and edges for a bipartite graph. The code simulates aircraft departure scheduling using a bipartite graph. MH, which is flights and time, are defined as two separate groups. Each aircraft is connected to its preferred departure time. Backup edges represent alternative available time slot. This alternative helps resolve conflicts when the preferred time is unavailable. The scheduling system can detect conflicts and reschedule flights accordingly. Step 4. Maximum bipartite graph of the allocation time to fly. The code assigns each aircraft a unique departure time using maximum bipartite matching. Conflicts are resolved by matching MH, which is flight nodes with time nodes. The method maximizes feasible scheduling solutions. Each aircraft is assigned one final departure time. The final allocation represents the most optimal and conflict-free schedule. Step 5 Summary of aircraft departing schedule illustrations. The code visualizes the final flight time allocations using a bipartite graph. Each aircraft is matched one to one with a departure time. Nodes are positioned clearly to show aircraft and time slot. Edges represent scheduling relationships. Matching edges show the final allocated departure times. Different color distinguish aircraft, time slot, and schedule. So here is the final graph after we solve it by using Google or our tools.
So, this is a final adjacency matrix that optimizes the flight schedule by ensuring a one-to-one mapping between flight number and time slot available. In this mathematical model, each row represents as a flight number, while each column represents as time slot available. Ultimately, this matrix serves as a strategic tool for air traffic management, transforming a potential crowd schedule into a clear sequential flow of departure time from 7:55 to 9:10 a.m.
Assalamualaikum, I am Nur Amira and I'll be presenting about illustration of the bipartite graph. Figure 1 shows a bipartite graph that models the forced reassignment of clashing flights. On the left, we have the set of flights, each represented by a vertex with a specific flight code. On the right, we have the set of departure time slots where each vertex represents a distinct time. In the graph, gray nodes indicate flights that are in conflict, meaning multiple flights are assigned to the same or overlapping time slots. On the other hand, red nodes represent flights or time slots that do not have conflicts, showing feasible assignments. This color distinction helps us easily identify which flight need reassignment. By presenting flights and time slot as separate vertex set, problem becomes a matching problem, where our goal is to assign each flight to a time slot without conflict. Overall, this graph provides a clear and systematic way to visualize and analyze scheduling conflicts.
In conclusion, this study shows that the original departure timetable contained overlapping times, even though the aircraft had different destinations. This overlap caused scheduling conflicts and reduced operational efficiency. By applying optimization techniques based on graph theory, specifically using bipartite graph and an adjacency matrix implemented with Google OR tools in Python, all conflicts were successfully resolved. Each aircraft was assigned a unique departure time, creating a one-to-one relationship between flights and time slots. This optimization not only prevents overlapping issues, but also improves the efficiency use of available departure slots. Overall, the results demonstrate that graph theory is an effective approach for solving real-world scheduling problems.
And this is the references. That's all from our group. Thank you for listening.